Next is the Inca Team from the National University of San Marcos.
Hello, everyone. It is an honor to present the work done by the Inca team for the final of the Frank Arnott competition, where we have applied the GUIU concept to exploration within the Yukon Plateau. Our multidisciplinary team is formed by Victor, a master's student from the University of Tasmania, Orlando and Juan Carlos, master's students from San Marcos University, Saul, Luis, and Yeldry, undergraduate students from San Marcos University, and myself, Sylvie, a master's student from Brigham Young University. In the background, we have Machu Picchu as an example of a successful Inca system, which was based on the concept of Ayu and Aini. Our main challenges were to integrate and validate big data sets, then to analyze them using conventional and non-conventional techniques in covered and non-covered areas. Our aims were to define robust exploration targets on a regional scale and then analyze their viability for further exploration. We modeled our methodology and teamwork around Inca concepts of social organization. IUs, which are small communities usually specialized in a specific task that are all connected through the concept of INI, which is the relationship of reciprocity among IUs of a larger community. In our case, each specialized area we call the GeoIU, which you can see located on each terrace to the right. On the left, we have the Tumi, a ceremonial Inca knife, which shows our workflow with each step that we took in completing this process, going from the bottom to the top.
Our technical methodology was based first on the 24 conventional targets, which is the traditional layer of GeoIU integration for observable target definition. Then the non-conventional techniques that is based on deep computing data analysis. Therefore, we use supervised fuzzy zoom and self-organized maps so that we decrease the possible bias. Then we got 18 new targets and we reevaluate existing ones. And then we did an analysis of the availability and social and environmental assessments so that we got 26 final available targets. Here on the conventional technique, we use in regional geology the prospective lithologies, the structure and lineaments, and the known deposits. Then the GeoIU remote sensing, which is based on the Aster and Landsat, both used for alteration, and then the Sentinel-2 that it was used for iron oxides. Then in the geochemistry of stream sediment, it was done with univariate and multivariate analysis statistics after the validation of the data. Here first we will see the local enrichment index and then the factorial analysis and range correlation coefficient. The last two are for possible polymetallic mineralization. Then in geophysics, the magnetics was really useful for the extrapolation of favorable lithological units and structures through cover areas. The main product, it was the tilt derivative, the analytic signal, and the reduction to pole. As a result, we got 24 targets with a certainty of 90%. This is obtained by plotting the targets against the known deposits. And finally, we rank all of them, as you can see in the bottom, the table. We rank them according to the individual analyzed variables and classified by priority and target type. Intrusion, related type, porphyry, BMS, and organic gold deposit. Well, here, using the fuzzy algebraic zoom operator, which is a supervised technique, we integrate the diagnostic factor maps on the left to produce a favorable predictor maps on the right column. First, the geological endowment, which includes the known deposits and favorable lithologies, and a buffer within the known deposits. Then the structural endowment, which is the map faults, the lineament density from the remote sensing and the basement magnetic lineament from the magnetics. Then the geochemical map, the same maps as we show in the traditional method. The alteration map based on the remote sensing Landsat and Sentinel, and then the magnetics, the reduced pole. Then we integrate using a fuzzy gamma operator of 0.87, which highlight better the potential target areas. Then we classify the map by statistics to get the anomalies. The level of certainty of this map is 90%. Well, here, the self-organizing map is a type of artificial neural network that is trained using unsupervised learning, which is a machine learning type. For this task, we perform first a principal component analysis so that we check some patterns from the predictor maps that we used in the previous slide before the machine learning process. Finally, using the k-means here, we define six domains, which explains 90% of the data, where cluster 2 and 3 has a closer spatial correlation with the known deposit. The final assessment and integration, we can see the initial 24 targets determined by conventional method, the fuzzy prospectivity modeling, the self-organized map, which apply machine learning, the self-clustering map. Then we integrate all the available information to define new targets or reevaluate existing ones, having as a result 42 robust targets with a 50% of certainty. Then we analyze the feasibility of the targets in the Yukon Quartz Plains, check the protected areas and First Nation land types, so that finally we got 26 available targets that are the red polygons. And in the best 4 targets, we did a further analysis, first an archaeological predictive modeling that is based on flat terrains and within 300 meters from a water source. Also, we did a 3D geological modeling, this to delineate the targets in a greater detail. For instance, this target 1 and 2 are intrusion related type, and 3 and 4 are copper, gold, moldy porphyries, right? Well, thanks to all the persons and company involved on making this possible. Thank you all.